Oh yeah, my name is Sonny Kim. I am, doubly assistant professor at Bothell. So today, my talk's title is Privacy Preserving Cyber Physical System Design. Specifically, I'm gonna talk about one of my research. So a homomorphic encryption-based adaptive image filter using division over encrypted data. So let's start. Okay, so in general, cyber physical system architecture or Internet of Things architecture consists of endpoint devices equipped with sensors such as camera sensor and end users who receive, analyze, or process the data and a network connecting the endpoint devices and end users. Here, endpoint devices can be a variety of electronic devices that we can easily see in real life. And endpoint devices is usually composed of a microcontroller with limited resources than a general CPU. So sometimes a cloud server is added to the architecture to perform some complex operations. And according to one paper, the number of things connected to the internet is expected to increase to over 20 billion devices in 2020, 2 years ago, which will generate a massive amount of data. And not surprisingly, privacy issues are rising. In particular, it is difficult to trust networks and clouds that are easily accessible to anyone. And one of the solutions is using cryptography. And one popular cryptography technique is AES, Advanced Encryption Standard. But there is a problem. We can protect private information on networks, but to perform some operations on encrypted data, we need to decrypt the data first. If operations are executed on a third-party server, such as cloud server, then private information is anyway exposed to the third party. And one solution to solve this issue is using homomorphic encryption, for short HE. And according to the Wikipedia, homomorphic encryption is an encryption form that allows computation on ciphertext without decryption. And the result is also in encrypted form, and decrypting the result provides the same or almost the same result as the computation is performed on unencrypted data. For example, 2 users want to sum up their salaries without revealing their salary information. To this end, they encrypt their salary information with some keys, specifically public key, and send them to a third-party cloud server. And then the server performs some homomorphic addition on the encrypted data and send the result to the users. The important thing here is that the homomorphic addition is performed on the encrypted data, and the resulting data is also encrypted. So the server cannot acquire any private data. The users decrypt the encrypted result with some keys, private key, and finally get the result. And the decrypted result is the same as, or almost the same as the result calculated on original plaintext domain, as mentioned earlier. And one possible homomorphic encryption-based real-world application is diagnosing diabetic retinopathy. So diabetic retinopathy is a disease that can lead to blindness when the blood vessels in the retina are blocked. For these diseases, patients regularly take and send their retina images so that doctors can compare them with abnormal, retina images to determine if they're actually diabetic retinopathy cases. And the problem is that these images contain some sensitive information. For example, retina images can be used for personal, verification. So how to protect that information is very critical in this application. And one study proposed the following system architecture. So first, so we can see number 1, Public key is generated by a hospital and transmitted to a user. And then the user's retina image is captured using the embedded system board. So here, with a special sensor, and the image is encrypted using the public key. And the encrypted image is transmitted to the resource-rich cloud server through a network, and homomorphic encryption-based image processing is performed on the cloud side. Specifically, this process extracts some features from the encrypted retina images. And then homomorphic machine learning is performed using the extracted features, and the result, which is still encrypted, is delivered to the hospital through the network, and decryption is performed using the private key owned by the hospital. And decrypted result is delivered to the doctor through a secure channel inside the hospital, and the doctor makes a final decision and delivers the diagnosis result to the user. And for future use, the diagnosis result is encrypted and stored in the cloud. So if you are interested, if you'd like to know more about this work, then please contact me. I can let you know the paper title. So from this slide, I'm going to talk about my research. So at Bothell, I have done some research for homomorphic encryption, and I'd like to introduce it briefly. The first topic is custom hardware accelerators for homomorphic encryption operators. Specifically, a big FPGA is used for this research. For example, I proposed custom hardware architectures of number theoretic transform, which is one of the critical operators in homomorphic encryption, and that is which is a variant of FFT, fast Fourier transform. Also, I proposed hardware architectures of fully pipelined modular multipliers for homomorphic encryption. Actually, this is my main research topic, and it is supported by multiple sponsors, such as NSF. And the second topic is privacy preserving real-world applications. For example, one Bothell, MSE student did research on privacy preserving convolutional neural network-based keyword spotting, and we recently submitted a paper using the results. And one Bothell undergraduate, specifically computer engineering student, did research on privacy preserving password strength estimation, and a paper written with the results was accepted to a conference this year. Lastly, Sharmila did research on a privacy preserving image filter, and a paper written with the results was presented at a conference last year. Today, Sharmila is attending this talk, so I will introduce this work today. So for reference, one Bothell undergraduate EE student, I think he's here, and I are doing research on custom hardware accelerators for computer arithmetic. Specifically, we are doing research on FPGA-based hardware accelerators of real number multipliers. And the result was presented at a conference. And in addition, its extended version was submitted to a journal. And lastly, I'm collaborating with some computer vision experts. And we recently published a journal article related to virtual keyboards based on deep learning. So anyway, from the next slide, I will introduce Sharmila's work about a homomorphic encryption-based image filter. So first of all, I will briefly explain the overall flow of homomorphic encryption-based applications. First, a number of input messages are packed into a vector, and this vector is converted into a plain text polynomial. This process is called encoding in homomorphic encryption. And in a homomorphic encryption domain, a polynomial is a basic data type. And then plain text polynomial is then encrypted into a ciphertext polynomial, and the encoding and encryption are performed on the client side. And the ciphertext polynomial is then transmitted to a solver through a network. And on the solver, homomorphic applications such as homomorphic encryption-based image filter is performed. And as mentioned earlier, operations are performed on ciphertext, so a solver cannot acquire any private information. And after the homomorphic application or homomorphic evaluation, the resulting ciphertext polynomial is sent back to the client and decrypted into a plaintext polynomial. And then finally, the plaintext polynomial is converted into a vector and users can see the resulting messages. Typically, this evaluation part, working on the server side, has much higher computational complexity. And there are some open source software libraries, such as Microsoft Seal and IBM HE library or HE functions. Basically, these open source libraries provide similar functions. For example, they have a key generation function, and the generated keys are as follows. Public key is used to encrypt the plaintext polynomial into ciphertext polynomial. And secret key is used during decryption to convert the resulting ciphertext polynomial into a plaintext polynomial. And relinearization key is used to restore the transformed data structure to the original one after homomorphic multiplication, because as you know, polynomial multiplications change structures of data. Lastly, Galois key is used to rotate data embedded in a ciphertext. In addition to the key generation function, some arithmetic operations and other operations are supported. For example, we can add two ciphertext to each other. Also, we can perform a subtraction between ciphertext, which is a variant of homomorphic addition. And we can multiply two ciphertext, and we can also perform multiplication between plaintext and ciphertext, which corresponds to multiplication by a constant. And using the generated Galois key, we can perform some slot rotation within a ciphertext. And this time, I will introduce image filtering algorithms, which are our target application. One of the most popular and the simplest image filter is mean filter. It just averages the pixel intensity values in a window. And it is well known to be effective in removing Gaussian noise and uniform noise, but it has the disadvantage of blurring on image. So to solve this problem, locally adaptive winner filter, for short LAWF, was proposed, which is our target filter in this work. And here is its formula. So local variance and local mean values are calculated in this in a window like this, and a division by local variance plus some constant is performed. As the local variance value increases, can you see my cursor?
Yeah, we can see it.
Okay, thanks. So this part approaches to 1, and therefore the filtered pixel value becomes close to the original pixel value. On the other hand, if local variance value decreases, then this part becomes 0. So the filtered pixel value becomes the average pixel value in a window. Since we can adjust the filtering extent depending on the local variance, it is advantageous in edge preserving. And a window scans an entire image, and local variance and local mean values keep changing. And the green colored speech bubbles make some issues when the original locally adaptive winner filter is moved to the homomorphic encryption domain. And here is the summary. First, conventional homomorphic encryption schemes do not support division between ciphertext. When I introduce the operations, addition, subtraction, multiplication, and rotation, right? Division there was no division. So division is not supported in homomorphic encryption domains. Actually, if a divisor is a constant, then we can calculate the inverse of the divisor in advance and convert the division into multiplication. But in the locally adaptive Wiener filter, filter window moves and divisor, changes continuously, so we cannot avoid division. So this is the first issue. The second issue is that pixels processed with each other in a window cannot be included in the same ciphertext. It is because we cannot perform homomorphic operation within a ciphertext. And the straightforward solution to this issue is to encode each pixel in a separate ciphertext. Such encoding incurs huge data size, which slows down the processing speed and increases the memory footprint and transmission bandwidth. For example, each ciphertext requires hundreds of megabyte data size, and if there are 128 by 128 pixels, then the data size is larger than hundreds of gigabytes. So to solve the first problem, the division problem, we applied a numerical method called Goldschmidt's algorithm. Let's suppose that y is divided by x. Then the Goldschmidt algorithm approximates 1 over x to a combination of additions and multiplications. And then dividend y is multiplied by the approximate 1 over x. Then division becomes multiplications, the combination of additions and multiplications, right? And the Goldschmidt algorithm is based on iterations, and as the number of iterations, denoted as d here, increases, the approximate 1 over x becomes closer to the exact inverse value. For example, 1 over 1.5, that is actually 0.66666, is approximated to 0.5 with just 1 iteration. But with 2 iterations, the approximate value becomes 0.625. And with 3 iterations, the approximate value becomes 0.6640625. So that is trade-off, accuracy versus computation. But important thing is we can perform division in the homomorphic encryption domain, not using actual division operation. And next, let's talk about the solution to the second problem, that pixels in the same window must be encoded and encrypted into separate ciphertext. So here is an example with the image size of 128 by 128 and window size of 3 by 3. So when the center of the window is placed on the pixel at 1,1, then the red colored pixels are included in the same window, right? Since they should be processed together, they must be encoded and encrypted into separate ciphertext. Okay, so we cannot avoid it. But the pixel at 0,3 is not included in the same window with the pixel at 0,0. So we can put the pixel at 0,3 into the same vector of the pixel at 0,0. Similarly, the pixel at 3,0 is not included in the same window with the pixel at 0,0, which means that pixel at 3,0 is independent from the pixel at 0,0. So they can be in the same ciphertext, okay? So if we apply this technique to all pixels in the 128 by 128 image, then we need just 9 ciphertext, which reduces the number of ciphertext of the straightforward method by more than 99%. And the proposed encoding technique generates another issue. In particular, a window moves, then positions of the pixels that need to be processed together become different. When homomorphic operation is performed on ciphertext, a slot-wise operation is performed, so the slot location must be same. But to To solve this problem, the slot rotation function, that is one of the homomorphic encryption functions, is used. And in the proposed encoding technique, only 2 rotation amounts are required. So the Galois key size for the slot rotation function is small. And the proposed homomorphic encryption-based locally adaptive winner filter was implemented as a client-server model. And for the client side, Raspberry Pi 4 Model B with ARM Cortex A72 microcontroller and 2 GB memory was used. And for the server side, a PC with Intel Xeon W2295 processor and 128 GB memory was used. And here is the entire architecture for testing. First, the Raspberry Pi board reads an image and adds some Gaussian noise to generate a test image. And then pixels of the noise image is encoded by the proposed encoding technique and encrypted into ciphertext. And the generated ciphertext are transmitted to a PC through a network. And then the proposed homomorphic encryption-based locally adaptive image filter is performed on the ciphertext. Actually, in Sharmila's thesis, another homomorphic encryption-based image processing application follows. But anyway, the resulting ciphertext is sent back to the client side. And after decryption and decoding, we can see the final denoised image. And to check the image quality, the denoised image was compared with the original clean image. So this slide shows the image quality results. To measure the image quality, peak signal to noise ratio, for short PSNR, was used. And a higher PSNR value means better image quality. And as references, the original locally adaptive winner filter and approximate locally adaptive winner filter that replaces a conventional division with using the Goldschmidt's algorithm were used. And these 2 designs are non-homomorphic encryption-based designs. For this graph, the x-axis shows 12 different images, 6 natural images and 6 medical images. And y-axis shows the PSNR value. The first thing we found was that for the previous approximate design and the proposed design, which are based on iterations, the PSNR values increase as the number of iterations increases. But when the number of iterations become 3 or 4, then PSNR values no longer increase on average. And the proposed design shows slightly lower PSNR results, 0.86 decibel, dB on average. And this difference is generated by a homomorphic encryption scheme itself. In our application, plain text messages are real numbers. So not to increase the ciphertext size, the homomorphic encryption scheme generates some errors, like in floating point operation. And on this slide, execution time results are shown. First, let's talk about the execution time in the client side, client functions working on the Raspberry Pi board. In total, the client functions take 19 seconds. In particular, encryption accounts for 55%. And encoding and decoding related to one of our contributions take about 8 seconds, which accounts for 42%. The execution times in client functions can be reduced by moving them to a resource-rich hardware platform. For example, when we perform these client functions on the PC used for the server side, they took only 2 seconds. So from 19 seconds to 2 seconds. The average execution time of the server function is shown in the bottom table. And for comparison, the results of the original locally adaptive winner filter and approximate locally adaptive winner filter are also shown. And for 9 ciphertexts that are a minimum number of ciphertexts for a 3x3 window, the execution time was around 8 seconds. The 9 ciphertext can include 8 128 by 128 images. So the execution time per 128 by 128 image is around 1 second. So compared to the non-homomorphic encryption-based designs, the execution time of the proposed design is much longer, but we believe that 1 second per image is practical. And also the result is obtained by using a single thread. So it can be further improved by using multi-threads. In addition, custom hardware accelerators can help speed up. So in this work, we moved a popular locally adaptive winner filter to a homomorphic encryption domain. There were 2 problems, and we solved the first problem by using a numerical method, and the second problem by proposing a new optimized encoding technique. And to the best of the author's knowledge, our knowledge, this is the first work that uses division over ciphertext for a homomorphic encryption-based image processing application. And we still have the slow processing speed problem. So to mitigate the problem, we plan to apply custom hardware accelerators for homomorphic encryption operators. So, yeah, so this is the last slide of my presentation. And do you have any questions?
I don't see any questions in the chat, Professor Kim, but if anybody has any questions, particularly about that research you just heard about, you know, feel free to ask. So I'll watch the chat, Professor Kim.
Oh, sorry. Okay. If there is no question, then we can move on to the next slide. So actually, the next slide is about our alumna, Sharmila. So yeah, I will briefly introduce her. So actually, here is her timeline. So she joined our MSc program in July 2020 and started doing research with me in October 2020. And fortunately, our paper was accepted in May 2021, and she presented the paper at the conference, August 2021, and she defended her thesis in December 2021. As far as I remember, the schedule was very tight. We were very busy at the time. Anyway, she graduated in December 2021, and she started working at Amazon Prime Air, February 2022. And as far as I know, she attended the WE510 probability and random process course, and 511 and 512 signal processing 1 and 2, and 525 and 526 embedded systems design and advanced embedded system design. So that's it. Oh, sorry. Yeah, so if you have any questions about my research, please email me. Okay, here is my email address.
Sharmila, was there anything you'd like to add about your research, in particular, your thesis, what it was like for you and what its focus was?
Yeah, so thank you, Dr. Graham, for the introduction and things. So yeah, my research was like the same thing what Dr. Kim explained. So that was the initial part of the research which we started to work on, and the thesis was a kind of extension of that research. So we added an extra layer of complexity to that. So In this, the first part of the research was more about filtering, and the second part of the research was about image comparison and thresholding kind of things. So the thesis was like the next continuation of the research, and we had like, yeah, very tight deadline. I was able to complete it. That's like it was good to do things more, and it was a good learning experience. Yeah.
Great. So could you tell us maybe a highlight of either the coursework or something you did in your thesis?
Yes, so the coursework was, I said that I took more of embedded system design. My focus was more embedded system design and advanced embedded system design. I was interested in FPGAs, so I wanted to do some hardware accelerator part, but yeah, without that, like we started to work on homomorphic encryption. That was really new to me. But yeah, it was very interesting to learn the things like the cryptography and how things work with that, and using images to to understand that. And also we had like how to process the encrypted data, and particularly images was a real challenge, and it was good to learn and understand the problems and get some solutions. Yeah, it's very good.
And how do you think your current role at Amazon Prime Air, how did the MSEE help you in that current role?
Yeah, so the MSCE actually gives you a more hands-on experience, and it helps you to dive deep into problems. So it's not like you just graze over a topic. You can like take any topic you want, and you can like dive deep and understand the problems, and you get more focus towards a single subject. And in MSCE we have like an option. It's not like restricted to a single topic. So most of the advanced courses, the professors allow you to choose your own projects, and you can like give your own problems, and you can work on your projects more related to that. And so it gives you more expertise to learn and understand things. And with the current technologies, like you will not be intimidated when you're going into an industry, so that you know where to look for resources, and you know the right direction of what you wanted to do. So that's one important thing I learned from MSc, and yeah, it helped me a lot in my current career.
Great. Thank you so much, Sharmila. So I'm just going to open up if anybody has any questions, or if you thought of anything that you'd like to add. We are here. And just to give you a little bit of information about the master's program that Sharmila did, you can do it full-time or you can do it part-time, and it's geared toward working professionals. So all the classes are, in the evenings, and it is really about taking your career to the next level. So if you want to learn more, you can always reach out to me directly, and we can always talk about that, and also about the coursework option or the thesis option. What is your best option? So I don't, Lacey, do you see any questions? Did I miss anything? Professor Kim, would you like to add anything, or Sharmila? Anyone have any questions? I guess now you're all ready to tackle cryptography. So does anyone have anything before I know it's Friday afternoon.
Actually, yeah, I'm not some cryptography experts. So my research goal is to implement some systems using cryptography, some privacy preserving applications, or accelerate the cryptography techniques, because specifically homomorphic encryption has a critical problem of slow processing speed. So by using some custom hardware accelerators, we can improve the processing speed. So that's my research. And actually, I'm not a cryptography expert.
Sorry to misrepresent that. So does anyone else have anything to add before we all have a great afternoon?
Yeah. So I saw the question. So how much could hardware accelerators speed up the processing speed? Actually, it depends on the design. But sometimes, for example, my hardware accelerators for homomorphic encryption operators speed up about 10 times. I forgot the number, but maybe 13 times. But sometimes if we can, actually if we design some custom hardwares on FPGA, actually the advantage is we can deploy many multi-cores and we can run them in parallel. And if there are a lot of multi-cores and if the input output memory bandwidth are allowed, then sometimes we can achieve like 1,000 times speed up. That is possible. Is it right answer to your question?
Hello, can you hear me?
Yep.
Okay, so hi, my name is Seunggeun Choi. I am also faculty here in electrical engineering program. And congratulations, Sharmila, for your research and your job at Amazon. Can you explain about your work at Amazon?
Sure, Professor. So currently, my work is FPGA engineer. So it's like more of working with RTL languages, and the current work is about like designing camera systems. So the FPGA kind of controls the sensor, and we'll be writing RTL coding for that portion of that thing. So that's the gist of the work.
Okay, so I guess your work at our school, our campus for your master's degree definitely helped for you to get this job. But what do you think about your future career, whether this degree, how this degree will help for you to, stretch your career furthermore?
Sure, yeah. So there's a lot of difference between doing a bachelor's and master's. So as said, the master's gives you more like a kind of exposure. You get to know more things about the particular subject. So you also know where to look for resources, and you get an idea of how to approach a problem. So that helped me a lot to in this job hunt and career search. And yeah, I think that learning will help me further in my career too. So how to approach the problems with different kind of things, and it gives a different perspective to dive deep into things and find the root cause of the problems, or root cause of something which you want to learn, those kind of stuff. Yeah, so that's a good thing about MSCE program.